Okay. So let's see if it's work. Yeah. So there is a little bit delay because of me, but I think it's fine. Yeah, so but first of all, let me introduce our group. So we are the robotics lab. So we brought two of our students here. So Aniket and Tom, feel free to talk to them after class, to know about their research. We also brought some of our robots here, so feel free to check it out. So we are a vibrant robotics group at George Mason, working on a variety of robotics problems, right? So we are also having lots of fun together as a group. Those are our ultimate activities. All these are our robots in the lab. We work together on lots of different robotics problems. But the overarching goal for our lab is to develop highly capable and intelligent mobile robots that are robustly deployable in the real world with minimal human supervision. So our methodology is always field-driven. So we want to put robots into the real world, into the field. And the technical expertise we have is in terms of motion planning to create very capable locomotors to move, on land, in air, and also at sea, right, in different places. And we have also been using lots of machine learning techniques to make those, motion planners to be more capable and also to be more intelligent to be in service of field robotics, right? So we have a lot of work in here, and in here, like the intersection between all these three here, right? We started out by working on a very specific field called disaster robotics. So as you can see here, so we want to use robots in the real world, in the field, to replace or to help like search and rescue robotics human rescuers. One example here is on the upper left. So this modular snake robot is being deployed in the Mexico City earthquake. So we work with the first responders in Mexico City, and then we develop our, locomotive reduction techniques to drive this robot fully autonomously without any teleoperators in the back end to go into those buildings to search for victims here, right? This is called locomotive reduction, and we use overhead security cameras to give the visual feedback to drive it. And you can see also in the middle here, you see this is the Greece refugee crisis. We use a robot called Emily. So it's basically a robotic boat to drive to the drowning victims. So right now, all the Greece refugee, all the Greece Coast Guards have to manually drive these robots to the ocean to drive to drowning victims, which have a lot of trouble with depth perception, right? Because they are standing on the shoreline, very difficult to drive it very far. So what we did is we paired this Emily robot up with an unmanned aerial vehicle in the sky, so that we can give the visual guidance to the ground, to the water vehicle, so the water vehicle can fully autonomously drive to drowning victims all on its own. And on the right-hand side, this is the Fukushima Daiichi nuclear disaster decommissioning task. So people sending this chatbot, a mobile manipulator, being teleoperated by like 3 or 4 human teleoperators, right? The problem with this is you send the robots in there, driven by 3 or 4 people in the back end. They don't have very good, situation awareness of the remote steam. So that's why people sending a second robot here, just to follow the first one. And the second robot's only job is to look at the first robot, the first robot here, to provide a third-person view, so that the first robot's human teleoperators can drive the robot in a better way, right? Apparently, the second robot is also teleoperated. You need another crew to drive the second robot to give the first teleoperating crew with better visual assistance, right? That is not very efficient. Cause a lot of trouble communicating between the two teams, and you need another robot, you need another team of human operators to drive the second one. So what we did in the past is we trying to, reduce the need of the second robot and also the second human crew with a fully autonomous, we call it tethered aerial visual assistant, which is the drone that flies around the ground robot, but with a tether attached to it. So the tether serves multiple purposes. So to match the power duration of the ground robot and the drone, because one drives for hours, the other can only fly for like 20 minutes if without the battery, right? So the tether is for battery duration and also for safety. It's very easy for you to retrieve the vehicle whenever it's crashed, because it's very, very dangerous, very, very difficult spaces in Fukushima. And also we have used this tether to localization. It's a very cheap way for us to have very precise localization without running, for example, visual odometry or SLAM onboard this aerial vehicle here. Then this vehicle is able to fly around, the ground robot to provide the better visual assistant, better viewpoint, so that the first robot's teleoperators can drive the robot in a more confident manner. So all these things are our effort in bringing robots into the field, especially into disasters, to make robots work better, right? But I guess this gives you an overview of what we did, in the past. But here, related with RoboRacer, we're going to talk about 2 orthogonal directions today in order to enable extreme off-road mobility. So one is called high speed. You want to drive, those are S110 vehicles, right? Everybody should be very familiar with that. How can we drive this as quickly as possible but also going through unstructured, unknown terrain. And on the right-hand side, this is another version of the F1 test, also one test vehicle, but more of a crawler version that can go over these very, very rugged terrain. We call it vertically challenging terrain here, right? So these are the three things we're going to talk about in today's lecture. So first, let's dive into the high-speed end of things, right? So driving a vehicle as quickly as possible. So the first work we're going to talk about is called learning inverse kinodynamics. So the objective is very simple. You ask the same thing as our RoboRacer, our race. You want to navigate a mobile robot to track the reference trajectory, your global path during deployment as quickly and as accurately as possible. So basically, this is simply minimizing a cost function J, including your total traversal time and your trajectory and tracking accuracy here, right? So total time and accuracy. However, unlike our current RoboRacer, the difference here is we need to drive this over all different kind of terrain, right? You can see there's all these different kind of off-road terrain. You need to drive them as quickly as possible, but also as accurately as possible. So we can put this under a classical, control loop, right? So we have our desired trajectory to track. We have a controller, issue our controls, which will take effect. That's your system, your plant, or your forward kinodynamic function, which will change your robot state, and you close the loop, right? So the problem with doing this in off-road environment is we have this unknown world state called W, which is caused by all these different kinds of terrain, which will influence our forward function, right? So that's very difficult for us to navigate very precisely and also very quickly. So this world state W is unknown. It will affect our forward function. It will also affect our controller, because if we are doing an inverse function, this W is unknown, so we don't know what should be the action to take to drive the vehicle. So our intuition for this approach for learning inverse kinodynamics is to, instead of using this unknown world state W, we try to use the machine learning to learn an observation function we call Y that is taking input of W and the robot state. And we want to learn this lower dimensional embedding that can be used by an all-terrain model to be used by our controller here. So one trick we did here, is instead of using this unknown W, here we replace it with our learned embedding Y here to capture the robot and the world state here in this embedding here. We can do it in a machine learning approach. This is more tangible compared to W here, right? So what is W? So for our first work here, what we did, W is a simple IMU readings, right? So gyroscope and accelerometer. So for this 1/10, autonomous steering vehicle, so controls input is very simple, linear and angular velocity or throttle and steering command. So we learn based on the last half a second IMU readings, we concatenate them, feed into our learned embedding, which give us a very low dimensional, two-dimensional embedding Y here. And then we concatenate our embedding with our desired state change rate, like the global path, our tracking reference trajectory here. We feed that into a learned inverse kinodynamic source function, which will give us the velocity and curvature value to drive the robot, right? How does this work? It looks very simple, right? So this is how it works on a multi-terrain track. So you see cement, you see grass, you see all the leaves, tree, twigs, roots, and all these combination of different terrains. As you can see, this is 1/4 of the speed, so it's slowed down by a lot, right? You can see despite all these disturbances from all these underlying terrain, the vehicle is able to drive at a very high speed, but also maneuver through without, colliding with the walls or without, getting stuck on the track. So both accuracy and high speed is maintained at the same time. So it works pretty well on our training environment, and we also tested it out on an unseen environment, which is an easy environment because this is more homogeneous wooden floor terrain here. Our model on the right has performed much better with finishing this loop at a pretty high speed without either colliding with the track as shown here or without getting stuck because it's not turning enough, right? So that is also generalizing to unseen terrain here, right? So to give you an idea how our experiment looks like, so we tried all different kind of speeds from 1.6 meter to 2.5 meter per second, right? So it's pretty fast for 1/10 vehicle on off-road track. So we compare our IMU inverse kinodynamics, IMU IKD work against two different approaches. One is a baseline. We designed the IKD model manually, and it's usually good for homogeneous terrain for low speed, right? That's shown in red here. And for this blue, it's an evaluation study. We use exactly the same training data, but we remove our dependency on our observation Y here, which is shown in blue here. And as you can see, with lower speed, all three models perform okay. They are all pretty, consistent. And if you increase the speed, all of them start to spread around. But as you can see here, in all these cases, the green is usually the most consistent and stay closest to the black reference trajectory, because that's the trajectory we want to track. That defines our accuracy here. right? Even though it is spreading also a lot when you increase the speed, that I think is still closest to the reference trajectory. And you may notice all these little dots at each of those terms. Those means how many times each model failed. Failure means you cannot make the turn, you get stuck, or you collide with the wall because you're driving too quickly, right? So mostly the green dots are smaller compared to the blue dots and also the red dots here, meaning our model is more successful in this off-road track here, right? So some numbers, I guess, basically the same failure rate, per speed on the left, also per turn in seeing environment and unseeing environment. So take home message is all these bars, the lower, mostly the green bars are the lowest, meaning our model succeeds the most and fail the least, right? But I do want to point your attention to one particular turn here, which is this turn 8. So if you look at this turn 8, our model is actually performing worse compared to the ablation and the baseline compared to the blue and red, because our bar is higher here. If you look closely at turn 8, so turn 8 is actually a transition point from a low friction, grass terrain onto a high friction cement terrain. So our IMU IKT model learns pretty well because when it feels it's on grass, it knows there's a lack of friction. So it learns to oversteer to compensate for the lack of friction between the wheels and the terrain. Unfortunately, because of actuation latency, because the vehicle is driving very fast, when it just enters this high friction terrain, the suddenly increased friction between the wheels and the surface will cause the oversteer to come in too much and oversteer the vehicle to collide with the inside wall very often. That is actually why our model does not perform well when you are coming from a low friction terrain to a high friction terrain. So this actually motivates our network because due to this inevitable latency in terms of actuation when we are driving at high speed, we need to consider what is the upcoming terrain changes. We will need to anticipate what we are going to be dealing with next, right? So this is basically the network. Instead of IMU IKD, now we have a VI IKD, so a Visual-inertial IKD. So the idea is to not only using our IMU, which is exactly the same as IMU IKD, now we are also adding vision terrain patches in front of the vehicle, so that both of them will be fed into our neural net, into our model here to drive the vehicle. So the result is better compared to IMU IKD. For example, IMU IKD does not deal with this transition very well, so it gets stuck on this track. Well, if we have a better, anticipation from our vision input, it can finish this entire loop without any problems here. So that means anticipation is very helpful when we are driving at a very high speed here, right? So learning via IKD works pretty well. It can address this turn 8, as we've seen before. We can make our green bar much lower, right? But another question we want to ask here is, because IKD, inverse kinodynamics, is inherently limited somewhat because it is always single step. I want to get there. What should I do now? Right? It is really sufficient if we really want to push our speed. So there's always some limitation of this, inverse kinodynamics here because it's too short-sighted, right? So sometimes it's not just about latency compensation. Even if you anticipate the next step, it's not enough. There's other things playing a role here. So it may be just too late. I will give you one example, right? If you are trying to go through the patch, if you go through it very quickly, you may bump too much because slowing down on one step is not enough. If you turn too aggressively, you may actually roll over the vehicle. That's an actual roll on our robot, right? And if you drive too quickly, turning too aggressively on this low friction grass, you may actually slide around very, very often. That's not good, right? So this motivates our network in this line of high-speed off-road navigation work. So we use forward kinodynamics. Because the goal, the benefits of doing forward kinodynamics is it can give us the ability to reason across multiple steps. You can roll out our dynamics many steps, so we can be more prepared beforehand, right? So this is our newest work called competence-aware high-speed off-road navigation. We call it CASTOR, which is an RL paper. It will be presented in a month in Atlanta in Accra here, right? We want to prevent all these things because only doing one step inverse kinodynamics is not enough for it to reason about the vehicle is about to roll over, bump too much, or sliding all the way around, right? So what we want is instead of single step ST to ST plus 1, we want to go back to the history or maybe going more into the future by H time steps here, right? Then our vehicle is no longer in 2D space because we need to worry about the rolling angle, bumping along the Z, and sliding along the Y, right? So our vehicle state is actually in ST3 for X, Y, Z, and RobotiXX. Our action stays the same, so linear velocity and angular velocity, or you can call it steering and throttle command here, right? So instead of doing an inverse kinodynamics function, now it becomes a forward one. It maps from the current state transaction to the next state. In doing this, we can do multiple step forward inferences, right? Of course, because we are doing off-road, it's also dependent on something else, as we talked about earlier, right? We know it's dependent on the IMU, as in IMU IKT. For forward kinodynamics, IMU also plays a role, right? We also know we need to look at the terrain visually. That's similar to VI IKT. Or for forward dynamics, we also need to consider our vision. And we also find out the speed of the vehicle at every time step is very, very important for us to reason forward kinodynamics. So we can build a representation of this multi-model input, including vision V, speed S, and inertia I here. Here we call it psi. Psi is basically a representation. We will tell you about how do we learn this representation that can be multi-model for us to reason about all these things together. And also a very good benefit of this is all these things are available here. And depending on whichever modality is available for you, you can just use a subset of them, right? What we find out is using, inertia is enough alone. Using vision and speed together is also enough. And using all three will give you the best results. I will show some numbers to validate that, right? But the key idea here is we can do multi-step forward kinodynamics by learning a representation, a multi-model representation of vision, speed, and inertia here, right? How do we exactly do this? So this is a representation learning techniques. So we call it TRON, terrain representation for off-road navigation. So it's a self-supervised learning setup. So using multi-model input. So we use IMU exactly as our IMU IKD work. We take gyroscope and accelerometer of the underlying terrain, right? So we also take vision. And one very special technique we did in this vision side is called viewpoint invariance. Because vision patches are very sensitive to all different kind of lighting conditions, right? So we want our vision embedding space to be very robust. So therefore, we use this special technique, visual invariance, by correlating the same patch but being viewed from different viewpoints. So visually they are different, but we know that's the same patch, but we can extract that from our autonomy data, right? This is the same patch viewed from this point, maybe darker, like viewed from the other point, maybe brighter. Maybe there's some shadow from one side, not the other. But they are the same patch. So we enforce these two to be similar because they are the same patch, just viewed from different viewpoints. So that's our vision here. And as we mentioned earlier, so we find out speed is very, very important here because it's the same terrain patch. You cannot reason about how this terrain patch will give you some kinodynamic response by just looking at the pixels alone. You need to know how fast you are driving on this. That's why speed is also very important. So VS is combined together. Of course, V1S and V2S, those need to be similar because they are the same terrain patch viewed from different viewpoints, right? Then we plug in these multi-model input into our self-supervised learning setup, right? We learn this vision speed encoder and inertia encoder here to give us our embedding here. So here is going to be psi t VS. This is psi t I, right? Time step t. This is the VS embedding. This is the I embedding. Then we know, if you drive on this patch terrain at this speed, you will experience this particular IMU readings. These should be the same. So this is where the self-supervised learning comes into play. We use a projector to project them into a high-dimensional space and use self-supervised learning loss. Like here, we use Barlow twins. BL means Barlow twins, right? We want to say, okay, these two things between these two vision speed embeddings should be the same. The first vision speed embedding and the inertia embedding should be the same, and the second vision inertia embedding, vision speed embedding, and the inertia embedding should be same. We're trying to say all these three things should be close to each other because those are exactly the same response we have. The same inertia we should feel when driving at this speed at this visual terrain patch. Also on this speed at this visual terrain patch. Then we can just use our Barlow twins loss to minimize the loss here. Then we can learn these two things to give us very useful representation of vision speed and the inertia here, right? Then that is basically the Barlow twins loss to minimize our cross entropy here. Right? So very, very straightforward self-supervised learning approach. So after learning that, these two things are learned. Those are things we care about the most, right? So that embeds your vision and speed modality. This embeds your inertial modality into some very, very useful embedding here. Then for downstream task, for us to do forward kinodynamics learning, we basically slap on a very simple NLP. We are only training this for us to predict what will happen next. And that can be done in a multiple step way, right? We're trying to predict what is the roll angle, what is the bumpiness, and what is the sliding. Or you can design your own metric. We call it competence awareness metric, right? Because rollover is not good, bumping too much is not good, sliding all over the place is not good. So that's why we designed these three as examples here, right? Then we can learn this for us to predict what will happen next in a multiple step setup here, right? Some numbers here. So the modeling accuracy. We compared against end-to-end approaches. So that is without any representation learning at all, right? So we use these different kind of modalities and combination of modalities: vision, inertia, vision speed, inertia speed, and vision speed inertia. This is basically everything. So that is the accuracy we achieve in terms of predicting roll, sliding, bumpiness, and all of them combined. We also compare against another state-of-the-art representation learning setup for off-road navigation, not necessarily high speed. There, for the Stirling method, they actually don't including speed because they are not aiming at driving extremely fast, not the same speed as we are driving at. So this is the numbers they achieve without considering speed. And as you can see, our terrain representation for off-road navigation work is achieving much lower, much lower loss compared to all these baselines here. The best result is achieved by considering all modalities here. So V, S, and I, vision, speed, and inertia. You can also only consider inertia because inertia on the terrain tells you about information about vision and speed, right? So that is pretty good. And you can also consider vision and speed. That is also pretty good because by looking at the patch, which is a viewpoint invariant, right? And by looking at the speed together, you can know how, how good, how bumpy, how rolling, how sliding your vehicle will be in the next time step. On the bottom, basically some qualitative examples here, right? We are trying to predict what will happen in the future. So green is our shown results, blue is ground truth, and Stirling is here, so it's showing in red. You can see our green line follows the blue trajectory very well in roll and also in sliding here as well, right? So as you can see, there's a very wrong peak predicted by Stirling here, and also for bumpiness. So our green line is closer to this blue line compared to the red one. Right? So meaning, qualitatively speaking, ours is also more precise. We put our whole Cosmos model in a human autonomy shared control setup. So human is driving here, so not a fully autonomous. But what we did is we put a Cosmos in the backend. So hey, we want the human to drive, but the human is very naive. It's a novice driver. It doesn't know not to violate all our competence aware constraint. The human may turn too aggressively and may, for example, here is rolling over the vehicle, right? Almost rolled over. The Cosmos is taking control in the back end, saying, hey, that is too much, rolling angle. That is too much throttle. That is too much steering. So slow down or turn less sharply. Here, Cosmos is saying, hey, human is about to enter a very, very bumpy terrain. It will slow down multiple steps ahead of time by reasoning about what will happen later. Similarly, this is sliding, right? Human is driving all the way and then like pushing the throttle to the floor and then, turning aggressively. But Cosmos is saying maybe you should reduce your steering angle so you can smoothly turn, or maybe just reduce the speed. All these are happening in the back end, right? How does Cosmos actually work? So this is a deep look into how is it working under the scene. If you look at the top scene, so that's the three scenarios: bumpiness, sliding, and roll you have seen in the previous videos, right? So those more dark lines are the human actual value being commented by the human. Human steering showing blue, human throttle showing blue, human steering showing yellow here, right? So all the dark lines. And what Cosmos is doing, it is doing his job in the back end, as you can see by those more shaded, like transparent lines here. So when it's about to enter this very bumpy area, so humans is not like slowing down at all. So Cosmos is saying, okay, slow down so that you won't bump too much on this rocky patch. That is what Cosmos is doing. So this is pretty simple, just by slowing down a few steps ahead, rather than just reasoning about one single step in our multi-step forward kinodynamic setup, right? In the middle here, so that is more interesting because the human is about to slide the vehicle on this low friction grass terrain, right? So as you can see here, the Cosmos is saying, hey, slowing down. At the same time, don't turn so aggressively because human is pushing the steering wheel to the one end, to the far extreme here, right? And then Cosmos is saying, hey, slow down, you can turn, but do it slowly so that we can actually minimize our sliding here. As you can see, the green line, which which captures how much the vehicle is sliding along the y direction, it is much lower compared to the red one without Cosmos, right? So this black line is basically our constraint. So we should not violate this line here by reasoning about our competence awareness. And similar thing on the right-hand side. So this is a high friction cement floor, right? The human is just flooring it, driving very quickly and also turning very aggressively. And then due to the high friction between the wheels and the cement here, the vehicle is about to roll. As you can see, this big red peak here. But if your Cosmos is saying slowing down and also cap your steering angle, the vehicle is only experiencing a little bit small roll angle showing as this green peak here. Right? So Cosmos can work well in a shared autonomy setup with a human driver. while the human driver is not competence aware at all. Well, Castle can give it the competence awareness needed to avoid bumping too much, avoid sliding all over the place, avoid having too much of roll angle and may damage the vehicle. So that works pretty well in a shared control setup. And we also put it on a fully autonomous setup here. So this is the MPPI planner, right? Model predictive path integral controller. So what we did is we put MPPI with Castle together. So this is robot top speed is 4.8 meters per second, almost 5 meters per second, right? We put the highest speed MPPI with Castle, and we compare against the highest speed of MPPI without Castle. That's the first line is about, right? So we compare these two to see what will Castle change on top of the highest speed planner here. As you can see, the top speed and average speed is indeed reduced, which makes sense, right? Because we are more competence aware. We should slow down whenever needed. So the top speed is reduced a little bit. The average speed is also reduced a little bit, but not that much, right? So from 4.8 to 4.0, that's top speed. Average is from 4.29 to 3.92, right? However, Castle is able to enable much better competence awareness. So the average bumpiness, maximum sliding, and maximum roll has been drastically reduced. Right? All these numbers are much smaller than this. That means without Castle, the vehicle experiences a lot of bumpiness, it's sliding all over the place, and it's almost rolled over. Right? So our competence aware metric is much better. We also compare against these two other state-of-the-art high-speed navigation baselines. So Sterling, which is the representation learning setup we talked about earlier, and also another 6-off high-speed off-road driving model called from Lee et al. Right, both on the highest speed. As you can see, the competence awareness metric achieved by ours is still the best among all three. Right. So we also want to show that Castle is not just blindly reduce the speed. Right, we want to show it is actually know where to stop, where to slow down, and where not to. Right, here we compared against another plan, the same planner, but with a much lower top speed. So we reduced the top speed from 4.8 to 3.0 meters, here. Right, as you can see, we actually can achieve very similar competence awareness metrics. We are actually slightly better than this. This means you have to reduce the top speed from 4.8 to 3.0. in order to achieve the same level of competence awareness. So Castle really knows when to stop, but still when to drive fast, because it may not violate our competence aware constraint, right? We also show that, if we combine Castle with this slow planner, right, we actually did not really reduce the top speed almost at all, right? So top speed is only reduced by 0.02, while average speed is reduced by a little bit by 0.07 here, meaning Castle does not just blindly stop, slow down the vehicle. It is going as quick as it can whenever possible, but only slow down when it is absolutely necessary because it wants to optimize all these competence aware metrics here, right? So Castle is not just blindly slow down the vehicle. So with this, I guess we covered the first direction, the high speed direction here. I guess maybe it's a good time for us to take a few questions if you have any about the high speed end before we move on to the vertically challenging terrain end of things. Any questions?
If you encounter terrain that you've never really seen before, even though the vision won't be able to know what it is it still pretty good at controlling it just from the IMU stuff?
Yeah, so I would say, I think, of course, every machine learning method have a limit on generalization, right? It doesn't work very well on all unseen terrain. So I think IMU is definitely much better compared to vision because visual appearances can be anything. Right, so I would say IMU is generally much better, and there's also a limit to the generalization of IMU. As you can see in this video, I showed our training terrain is off-road course, and we show it generalized to an indoor wooden floor. That's actually my living room, right? So it's working pretty well, but that means it's an easier terrain, right? I don't think if you bring it to a more complex terrain, it can generalize because if I've never seen the complex terrain, it doesn't know how to drive on it, right? So there's always a limit to generalization. Yes. Any other questions about the first high-speed thrust?
So one question I had, when you're training, right, you show the manually driving portion. How else do you collect training data? Maybe you covered it another.
Yeah, so we actually, so it's the same thing. We basically manually drive. So doing all the aggressive maneuvers. Yeah, one interesting maneuver, we have to do for this rolling. It's probably too difficult for me to go back. Yeah. For this rolling, it's very difficult for us to collect the data. So Aniket and Anush, so they have to drive the vehicle very aggressively to get, I think, 40 rolling points. and risk actually damage the vehicle. Yeah. So it's not easy to collect data for those extreme cases.
And then when you compare, like say to the Sterling, some external work, right? They have tested it on some other terrain. How do you, like then you have that code and then you test it
Yes,
out?
yes, we reach out to the Sterling. Sterling is from Peter Stone's group, right? Horizon
yeah.
work. We have their code, so we test it on it. We train with our data. That's what we did.
So you have like apples to apples.
Yes, yes. Yeah, and of course, Sterling, to give them credit. So for Sterling, they're not aiming at high speed. They're aiming at, I want to avoid this patch of terrain, but to go into the other patch, right? So it's more like where to drive, but we are more interested in how to drive.
I have a question about the slide, I think number 8.
8?
So yeah, one of the introductory slides. So the maybe I missed it, but I want to understand more about what type of controller, how this controller is modified by the terrain model.
Of course, this slide is very, very abstract,
Yeah.
right? So previously, what people do is this whole closed loop control setup like this, right? So you can do any controller. For here, what we did is we have a reference projection we want to track. We want to get on the next waypoint, and then what do you want to execute your controls, right? For us, it's a sampling-based method. We pick the best one and move you as close to the goal as to the intermediate goal as possible, right? So that is our controller. But you can apply this into any controller.
Like for example, if you consider like a nonlinear control where the world state is also modeled through the information you get, and then you modify the analytical equation of the
Of course,
controller.
you can do that as well. Yeah.
Yeah, that I think is a new idea for.
Yes. Yeah, that would be yes. Any other questions?
Yeah, one more question.
Do you do any fine tuning with the data that you get after you've trained, or do you just keep the model as is and you just do all the control with it?
Fine tune. So we get the data, we train it, and we deploy it.
Right. So let's say if you when you deployed it on a new terrain, did you retrain with the data? That
We actually, so for this experiment we show in this video here, so we actually did not. So, but as I mentioned earlier, right? So here, so for this part, we have this is unseen terrain, so we did not fine tune. But as I mentioned, we for full disclosure, this is the EDA terrain, right? So this is not even off-road.
Right.
If you go to a more challenging terrain, I don't think it will work.
Okay.
Right. So, but by this we are just showing we have not seen this very flat, very friendly terrain, but we can also generate that to it.
Have you tried adding the data that you collected from this unseen terrain and see if it still improves for that terrain or no?
My guess is yes. We haven't tried that, but my guess is yes. Right? If you can fine tune it, it's always going to be better. Any other questions? Yes, before we move on to the last one, to the vertical challenge terrain. Not, because we are halfway done, so I guess halfway up in the time, which is perfect timing for us to go through the second thing. So now let's switch gear a little bit. Instead of going fast, let's try to be more, going through extremely rugged terrain. So that's what we call vertically challenging, right? So you want not only to go fast, but also try to not roll over, as you can see in one of the bad examples here. You want to plan the path so you can minimize your roll angle, but also avoiding getting stuck. You don't want to get stuck between two big rocks, right? How do you find the path, and how do you control? How do you drive it so you can smoothly go through this environment here? So, I want to first give an overview of a lot of things we have done around this whole vertically challenging terrain problem, right? So you want to avoid that from happening, right? So first of all is platforms. So we have 2 of those here. Feel free to check it out. So those are things we call verti-wheelers. So it's wheeled mobility for vertically challenging terrain. So verti-wheelers. So we have designed a 4-wheeler. As you can see, 2 of them here. We have designed a 6-wheeler as well, right? We also have a tractor-trailer system. You're pulling a tractor, trailer at the end, and we also replace the wheels with tracks. So instead of 4 wheels, we have 4 tracks here, which I will show a video later. So we have the platforms we built. So that is, the verti-wheelers. And another infrastructure we have built is try to benchmark the mobility on this extremely challenging terrain, which we call the verti-bench. It's a benchmark developed by Tom here, right? So we consider geometry, semantics, obstacles, and also scalability. So our simulator based on Chrono can be scaled up and down to 1/10 vehicles and also to a full-size vehicle if you want. You can see this is like a tank, like a tracked tank here. So it's a full-size tank. You can scale your environment up and down to benchmark them as well. I will also show some videos of this. So this is the Verti bench. And we also do a lot of like kinodynamics learning, planning and control work on this, right? So this is our first work called WMVCT, again, wheeled mobility for vertical challenging terrain. What we did is we decomposed a six-stop model into 3 parts. Optimal steering, elevation map for Z, and neural net prediction for run pitch, and we put it into a planner, which I will go over in a little bit more details in the following slides. So that's our first planner we developed. And the second planner we have done is, this is the full 6-stop model. So the previous model is based on decomposition. Here, this is the full 6-stop model. But the key is, how do you make it more efficient? Because this is a very complex model, and you need to, in a self-based motion planning, you need to query this model thousands of times, like in a second. How do you do that very efficiently? This is called terrain attentive learning, or TAL, TAL. So this is pretty good, but still, if you have a very heavy duty model, you don't want to waste all your compute on querying some terrain which is obviously not traversable, right? So that motivates our next work called TNT. So traverse the non-traversable. So we want to first filter out all the obviously non-traversable terrain and only save our compute, our very heavy duty compute, our heavy duty planner and the model on those promising terrains to figure out how to drive over them. So that is TNT, traverse the non-traversable. And in addition to classical, modeling and planning and control, we also have a lot of machine learning approaches. So this is also Tong's work here called Verti-selector. So this is a curriculum learning for reinforced learning setup. So we want to build an agent that can teach our Verti wheeler which is the right terrain for the robot to learn based on its current capability. So curriculum learning, Verti-selector. So we also use a lot of the state-of-the-art, those like transformer-based method as well. So Verti-coder, this is the paper which will be presented next month at ECRA. So we basically use the vehicle pose, action, and the underlying terrain patch. We put that into an transformer encoder, and then we will be able to reason about what will happen next. And we can use an encoder to do a lot of different kinodynamics downstream tasks, which I will also slightly go over this in the next few slides. And this is only the transformer encoder. We also have a work that put the entire and transformer, including both encoder and decoder together, and to enable multiple downstream tasks during one training session. We don't need to train for multiple downstream ahead. So this is our Verti formal work, a full-scale transformer using only 1 hour of data to train the vehicle mobility on this kind of terrain, doing both behavior cloning, forward kinematics, inverse kinematics, and terrain patch reconstruction. And the last thing we have done in the past is, it's called control barrier function. We want to assure safety when we drive on these terrain. We want to avoid these things from happening. What is safe and what is not safe to drive on? Usually control barrier functions only deal with collision and non-collision, right? For us, it's more than just collision. It is about when you roll over the vehicle or where you get the vehicle stuck. How do we learn a terrain, a control barrier function on top of that? That is our latest work. It's still on the review this paper. So TCBF, terrain-based, traversability-based control barrier function here. So that gives you an idea of like the variety of work we have been doing in this whole ecosystem, including infrastructure we built for this Verti wheelers ecosystem. We have a lot of kinodynamics modeling and planning work under this, and all these 4 things are basically off-road mobility learning, more from the end-to-end learning side of things, right? So I guess let's talk about this infrastructure first. So for the platform and also for the benchmark, right? So this is basically you have seen two 4-wheeler here. So that's the Verti 4-wheeler. With differential locks for the front and rear axle, and also low gear and high gear, and you can go fast. You can also start to crawl. And we have built, as you can see, this is a tractor trailer system, and also we replaced the wheels with tracks to study the different embodiment, different morphology, how that will influence our mobility. All these are open source designs. You feel free to take a look at these. Right, so those are our systems, our platforms we built for this whole ecosystem. This is a Verti bench. How do we benchmark? So right now, benchmarking off-road mobility, every group have their own robots, have their own test terrain. But we ask the question, how can we objectively and quantitatively evaluate off-road mobility in a very standardized manner? So this is our Verti bench approach, right? So what we include is first elevation. We want to have different kind of elevation from low, medium to high. We want to add semantics, including rigid terrain, deformable terrain, and a combination of rigid and deformable potential together. We also want to add obstacles, right? Boulders, rocks, trees, bushes, including sparse, medium, and dense obstacles, right? And then we randomly sample across all these kind of different, 3 dimensions, right? So from elevation, semantics, and obstacles. Then we can create a lot of these, off-road environments here. So we have 100 of them. Of course, the code is fully open source. You can generate more if you want, right? For each of the environments, we sample 10 different start and go pairs that compose 1,000 navigation tasks. So this is our benchmark. We want to give you a very standardized platform so you can benchmark your mobility in our 1,000 environments here, right? This is one of the Hummer, so full-size vehicle driving in the sandy terrain here, getting stuck by the wheel, by the rock here, right? We also have other vehicles like this 6-wheel truck, this tank, this 1/5 scale vehicles, and also we have 1/10 vehicles as well. You can scale up and down as well. We provide some initial benchmark of almost all the available off-road mobility system we have done, including hybrid, end-to-end, and also fully classical. The initial metrics we come up with for our problem is success rate, traversal time, and the roll and pitch angles here, right? So we also have some physical validation we run on our 1/10 vehicle. That's the digital twin we built by scanning all the parts and trying to measure the suspension properties and everything. So basically, it's very similar to the real world. Of course, there's still to gap, but we're trying to really minimize it. As you can see, the vehicle gets stuck in here. We also get stuck in here, right? So that's like a cross-platform validation. So that's a full-size vehicle getting stuck by this rock here. This is our 1/10 vehicle here. The verti-wheeler also gets stuck in our indoor test bed. So verti-bench. So if you want to benchmark your mobility, check it out based on a high-fidelity simulator called Chrono. So now we covered all the infrastructure we built for this verti-wheelers ecosystem. So let's talk about kinodynamic modeling and planning. I think that's probably my favorite part right now in this whole system here, right? So let's first look at the problem, because we have covered the basic, high speed. So for 2D navigation, usually the problem is very straightforward. You have your free space, obstacle space. The goal is trying to drive your vehicle in 2D, right? So in SD2, X, Y, and yaw, using your throttle and steering command, right? As we say, we can do forward kinodynamics, give you the next state. You don't need to consider anything else, because if it's a flat ground, you just need to consider your state and action, which will give you next state. The goal is try to drive through, avoiding all these obstacles, right? So that's the classical things. Even we do this for our high-speed off-road navigation thing, right? Here, our problem is different. So this is the problem formulation for this vertical challenge terrain. So we still have free space and obstacle, but the problem here is not to avoid obstacles, because if you want to avoid obstacles, everywhere is obstacle. There's no way you can drive through, right? The goal here is, we still want to use our same action, throttle and steering command, to drive a much larger state, which include X, Y, Z, roll, pitch, yaw in SD3, right? And then our forward kinodynamics function is more complex, not considering current state, current action, and also needs to consider something about the environment, very similar to our high speed direction, right? Now we need to consider explicitly about the underlying terrain here. Here we denote it as M, showing red here, like the geometry, the semantics, everything necessary for you to reason about the kinodynamics interactions within this red region here, right? For now, we have mostly considered elevation or geometry information here, right? So now we want to plan in SD3. We do kinodynamics planning in SD3. So the first work we have done here is our very first planner, our very first kinodynamic model we have done is, using based on model decomposition, because decomposing gives us efficiency. That's the key one we want to achieve here. So we leave the X, Y, and yaw to an Ackermann theorem, or you can use a bicycle model as well. Very simple. Assuming it's a flat ground, you can query those very easily, and you can even pre-compute them very easily, because those are not determined by the elevation underneath, right? So, but that is very fast. And then we leave the Z value into the pixel value of our elevation map. So each of the Z will have a corresponding height based on the elevation map we built. We leave the Z to it. And then for the roll and pitch, that is the more difficult part. We use a data-driven approach. We're trying to learn the roll and pitch angle based on our elevation patches underneath the vehicle, right? So after this, we put everything together. After decompose, we put everything together as the whole 6-stop model in SD3 here. After decomposition, right? So then we can do planning in. You can use any planner you want. We use a custom built planner in this work, but what do we consider in SD3? So those are new things we need to consider, in SD3. For example, the cost of rolling over. For example, the cost of getting stuck in mobilization here. Those are actual costs we need to consider, which is not necessary when we're driving on flat ground, right? Cost of height change. You don't want to change too much height in 1 or 2 steps, right? And also the normal things. You don't want to drive out of the map boundary. You want to have your estimated cost to go. All these are the things you consider in classical and 2D planning as well, right? Then we can produce a path considering all these costs. You use whatever path planner and motion planner you have, and then we can use the PID controller, very simple to track that path. So this is the very first work we have done. So give you some idea how it works. So we tried it on 2 different robots, the Verti 4-wheeler and Verti 6-wheeler here on this indoor test bed in our lab, right, with a lot of rocks, right? So if we don't do, the baseline, we don't really have much baseline back then. So the baseline we have done is behavior cloning, basically end-to-end learning without explicitly considering the model here. So BC fails, as you can see in red here. So the roll and pitch angle, of the red line is usually larger compared to our decomposed model. Our decomposed model is showing green here. So it's much smoother and it gives you a smaller roll and pitch value and more successful here. So this is the first work. So it works okay, pretty good. But of course, there's still a lot of room for improvement, right? One of the most straightforward room for improvement comes from this 6-off decomposition. We do the decomposition for efficiency because we need to query our model many, many times. We cannot afford a very large model, right? But after you decompose, you will introduce unnecessary errors here, especially from this simple argument theory here, right? So close is simple and efficient, and you can even parallelize the roll and pitch prediction based on neural net for all predetermined terrain patches because you know the XY yaw based on a fixed outcome model. That is good, very efficient. However, the concept is also very, very obvious, right? XY yaw do not actually follow outcome steering model because the vehicle actually work on vertical challenging terrain. So outcome model is not precise at all, far from being precise. So that Z, roll, and pitch accuracy will be degraded because you're not even on that XY and yaw. Your terrain patch won't be precise, your roll and pitch angle won't be precise, right? So what we need is we want to model XY yaw for vertically challenging terrain as well. Don't just use a simple dumb outcome model here, right? So XY yaw should not be predetermined. You want to decide what is the next XY and yaw across time. But we need a way to quickly attend to the next terrain patch based on the XY yaw very quickly because that model needs to be queried many, many times during sampling-based motion planning. Right? So we need a way to quickly attend to the next terrain patch based on the last data action transition for the next model query. So this motivates our next work called TALK, so terrain attentive learning. So we are using this representation learning techniques again. On the right-hand side, this is our pre-training, right? So we have our whole elevation map, a large map of the environment. And then we want to know what would be the kinodynamics on a particular terrain patch defined by X, Y, and yaw, right? For example, this red box here, right? For this terrain attentive learning model, what we are learning is given the whole terrain, which we embed into this ZM here, is if you do the cross product with our terrain attentive encoder X, Y, and yaw, it will give us, it will reconstruct this small patch right here, right? The way of doing this is because all these are very large, this is a very large neural net, right? So we cannot query this 1,000 of times during deployment, especially not in a parallel way, right? But this is a pre-training. After we learn this, we can enter we basically get these 3 things trained. And then this thing is actually frozen. We don't need to train anymore. And then here during deployment, you can see on the, so basically you have the encoding of the whole map, a very big map, encoding into a very small embedding here, small embedding for your terrain attention, right? Then you cross product them will give you everything you need to reconstruct this terrain. So if you want to read about kinodynamics at one terrain patch, at this terrain patch, the only thing you need is this guy here. Right? It's a very low dimensional thing, which you can query many, many times. And then during deployment, we don't want to, all these are frozen because we have to train this here, right? For the deployment, we don't want to query this many times as well, which is possible since this whole big map is not updated very often. It is probably updated like once a second or maybe at 2 Hertz, not very often. So this only need to be queried once or twice a second. That is okay. Then we have our embedding here. We take the cross product. All these things are much smaller neural net. And these things can be queried like 1,000 times. All these are very, very small ones. And we train a state action encoder. So to give us the full kinodynamics, we train our kinodynamics model as downstream task. This is still frozen because we have pre-trained this here. Then we can train these. All these are very small, so we can quickly give us our next state very easily based on a very efficient representation of the whole elevation map, right? So that is very precise because it is reasoning about 6 stuff. That is also efficient enough so we can query this in real time, right? So those are all very small things so that we can efficiently query them. So how is the accuracy look like? So to give you an idea, so those are the modeling, accuracy comparison between TAW and WVCT is our previous decomposed model. You can see along XYZ European jaw, the decomposed accuracy is very, very low. The error is very, very high, while the green is much lower, which you can also see for in terms of prediction step, right? Because our Ackermann's theory assumption in the decomposed model, the error in terms of, this is a positional error and angular error grow very quickly, while using the TAW model, it does not really grow that much. As you can see qualitatively, the green line also stay very close to ground truth, showing in blue, and the red line, which is the decomposed line, actually go even out of the map boundary. So we integrate this with the MPPI planner. So this very, very precise model that works very well, right? At least give us very high accuracy, as you see in the last slide. So however, what we observed is there's a mismatch between high model accuracy, as you see in the last slide, and good planner performance here. So it does not really outperform WMVC. They both succeed 10 out of 10 trials. So what is the reason behind this, right? Why high accuracy does not translate into our high performance, our high navigation performance, right? So what we observe is, if you use a very high precision model, which is slower, even though you can query it in real time, it is much slower to converge. So there's a trade-off between model accuracy and query speed. You may want a higher accuracy, but if it's very slow for you to query it, it may very slowly converge and does not give you good performance. But on the other side, if you have a very simple model which can be queried very quickly, but model is not accurate, that also may not give you good performance here, right? So this is also brings up us to this idea of like quantitative versus qualitative kinodynamics modeling. Right. So so some terrain are so challenging that we know is not traversable to begin with. Why do we need to spend our effort querying our very expensive model on that? That's just a waste of our compute, right? Some of the terrain looks promising. That's where we want to spend the effort figuring out what's the best way to drive over those, right? So this is qualitative versus quantitative understanding of the kinodynamics, right? Can we do better? So based on this idea of quantitative and qualitative kinodynamics understanding, we have a new approach. This is the TNT work we have done, right? So this is what TAW is doing. So if you have a very, very large rock patch over here, it is obviously non-traversable. You don't even need to try here, right? It's a huge rock. But if we use the TAW model by randomly sampling or sampling guided by MPPI, it may blindly sample lots of trajectories going through this obviously non-traversable terrain. You are wasting a lot of time. Of course, this is still traversable, but this is actually not the good one. You all know we should go around here, right? So that is just waste of the compute, even though the model is accurate. So can we do better here? So this is our next step. The next step is actually a precursor to our sampling-based motion planner, which is called traversability estimation. We want to filter out this, white region, which is obviously non-traversable, and don't spend our compute on there. Let's spend our compute on the more promising ones. So these blue regions compared to this green one, that looks more promising. Let's not waste our compute on here. Just try to sample here to figure out the best way to drive through here. And remember, so this looks easy here, but this is actually still very challenging. Those are still all the rocks here. Here, that's a big boulder. There's no way you can drive through. Don't waste compute, right? Here, it is still challenging. You cannot just drive over here. You still need to figure out how to precisely, efficiently drive through here using our learned very precise 6-stop model here. So that brings us to this TNT work, traverse the non-traversable, right? So the key idea here is we want to distinguish the potentially traversable from the certainly non-traversable areas. We don't want to waste compute on certainly non-traversable areas. And potentially traversable areas still may not be traversable, but that's where we use our heavy-duty planner, our heavy-duty 6-stop model to figure out whether they are actually traversable or not, right? But how do we measure traversability of vertically challenging terrain patch? P. Question.
So what look ahead distance do you have right now with this?
What's the look ahead distance for here, I guess, for this? This is probably 1 meter?
It's
How many steps?
right now it was 18 steps.
18.
So based on the velocity sample, it can vary. But in general, it would be around 1 meter.
Just 1 meter.
Yeah, 1 or 2 meters, like a reliable one.
So, but what if you have occlusion, right? I mean, you have the rocks are right in front of you.
So right now that is still a problem. The way we handle this is whenever there is occlusion, the grid map or basically the elevation map package that will have pole or NN value. For the time being, we just fill it with the lowest value, seeing that is as uncertain. But over the period, when you go ahead and ahead, usually that occlusion will go away somehow.
But the terrain is not previously observed.
No,
You don't have
that
any
is
map.
not previously.
This map is being built on the fly.
So when you're training your networks for this, how sensitive is it to like the dimensions of the vehicle, the dimensions of the tires?
Mhm.
Like that, right? So because what if you, like, for example, there's a certain like dimension based on your vehicle's wheel size and suspension, there's a maximum dimensions that you're able to traverse.
It is very sensitive. For example, the six-wheeler which we didn't bring here, which is this long, much
Yeah.
bigger one.
Yeah.
This terrain will be like very, very easy for the six-wheeler. You don't even need to look, just drive. It will go through. It's very, very sensitive. So that's also why the TONS research direction is looking at this cross-vehicle mobility. How do you figure out this patch of terrain is traversable for A but not for B? How do you quickly adapt? Right. So that's another thing. Yeah. So
But this training is very much like trained for this
for
particular.
the particular
It's
vehicle, yeah,
specific
yeah,
for
for
the-
specific vehicle,
I
yes.
assume that. I'm
Yes.
just-
That's also why TON have this verti bench.
Yes.
That give us lots of different vehicles. We can collect data very easily from the simulation. Right? So I guess, yeah, moving on here. So I guess, how do we measure the traversability of vertically challenged terrain? Why do we call it traversable, non-traversable? Because there are lots of traversability estimators out there, right? Because if you put our terrain into the traversability estimator, the answer is very simple, non-traversable. Everywhere is non-traversable. How do you go with that, right? So that's why we call it traverse the non-traversable. How do we measure the traversability of a non-traversable vertically challenged terrain patch P here? That's the goal we are trying to achieve here, right? So we propose a bunch of dimensions to quantify traversability. So if you put the vehicle on a terrain patch, you can compute the roll and pitch angle just by assuming there's no suspension. Let's just assume it's a rigid body. We put the vehicle on there, we can compute the roll and pitch angles. The larger the roll, the larger the pitch, the lower the traversability value is, right? So that's very straightforward. We also find out this, we call it velocity discrepancy. It's also very helpful. So if you command the vehicle to drive at a certain velocity on a patch, but the actual velocity is very, very different, that means it is not very traversable. If it is very same, most likely it's a flat ground, so that's highly traversable, right? So and also the other thing is we cannot, because given the terrain patch P, the velocity discrepancy is also dependent on how you drive your commented velocity. There's no unique answer here, right? That's why we need to model this as a distribution. So we model this as a Gaussian, so mean and variance of our velocity discrepancy, because that's not a single value here, right? Similar idea, so we call a post prediction discrepancy. So using our best model, right? So you can predict the pulse on that vehicle. If you can precisely predict the pulse on that patch, great, that's probably traversable. If you cannot precisely predict it, that's going to be not very traversable. Again, it's a distribution rather than a single value here, right? So given a patch, I have a distribution of discrepancy here on this particular patch in terms of mean and variance, assuming it's a Gaussian. Then all these three things can be combined. Of course, there's some fine tuning here because how should they be combined? There's some ways we have to manually assign, but that gives us a way to quantify the traversability of non-traversable areas. So the whole pipeline looks like this. We built our elevation map. As you can see, as Rahul mentioned, there are holes in here. All these black ones are holes because we don't know the value for those. But that is okay because when we drive over here, you may see this. It will get updated, right? The whole training pipeline looks like this. We randomly crop lots of different, terrain patch P here, right? So we can compute the roll and pitch based on our physics-based model, assuming no suspension. We can compute the roll and pitch. And if we do this many times, it will give us a heat map in terms of roll and pitch angles, right? So this patch, this pixel corresponds to the value of this pixel for roll and pitch, right? Similar thing for our velocity discrepancy, we can also do the same thing. This patch, considering to this pixel here, we can compute the mean and variance in terms of linear velocity and angular velocity. That's a 4-dimensional vector here. We can also do the same for our post prediction discrepancy here. So if you predict the post using our best model, if it's uncertain, then you should do then it becomes highly non-traversable, right? We can have mean and variance. We didn't choose all the 6 dimensions of the post. We picked a few of them, which are most useful for us. I think we pick 4 of them. There are 18 here. Mean and variance are 4-dimensional out of our 6-dimensional state space here. And then with all these heat maps, we can combine them together with some weights we fine tune. And all these weights are actually not single values. Those are actually vectors because you need to assign 2W for roll and pitch, 4W2 for all these things. But these are vectors as well. Take the dot product, and then sum them up. It will give you the final traversability map. Then the last training, This is our patch-wise traversability value generation. That is our traversability value. Here, you can probably see this is more traversable compared to all these red regions here, right? Then the last step is the green piece, map-wise traversability map reconstruction. Because what we eventually want is we want to see this, we want to predict this. That is a pretty easy prediction problem. If we generate data through this, we can have basically a regression, a supervised learning task to predict from our elevation map into our traversability map here, right? So then that traversability map basically gave us a guidance of where you should sample and where you should not sample, because our sampling is very, very expensive due to a high dimension, due to a high DOF model here, right? So now we have all three things combined together. We put TNT first, try to evaluate the traversability, and then limit our sampling, our tall model only on the promising areas, not the obvious and non-traversable areas, and then put it into MPPI, right? So this is one example you have seen here. So not using TNT, only use the tall, because the slow convergence actually gets stuck here and then roll over, right? So here we actually add the TNT on top of our tall here. So we know don't just bother sample here because it's obviously non-traversable. See all the green here. You should sample around here. Then it is more efficient. It will converge much more quickly and can drive through very easily, right? We use TNT to bias MPPI sampling, so we can save computation from sampling and model query on the certainly non-traversable terrain, right? So we don't need to bother to sample here, right? And then we only reserve the high precision tau model query on potentially traversable terrain. Even though those are potentially traversable, they may not be traversable, but we need to figure out by using our high accuracy models here, right? We compared, in terms of success rate, adding, TNT give us the best result, success rate. Conversion time is also reduced because it converges faster, right? We have lower roll and pitch angles, and also our throttle and steering are even more stable here. So that means we can actually driving more smoothly because our faster convergence guided by our TNT, guided by our traversability estimation here. So I guess this basically wraps up the second thing. So kinodynamics modeling and planning. I think we should have 20 minutes. So I guess I want to quickly go through the last more towards the end-to-end mobility learning side of things, right? I'm only gonna go through, I think, these two words here. So verticoder, so transformers, very, very successful architecture in terms of large language models, right? All ChatGPT are enabled by transformers. So we want to apply that to our kinodynamic, mobility tasks as well. So the first work, which will be presented at the ECRA in a month, called verticoder, self-supervised kinodynamic representation learning on virtual challenging terrain. Okay. So usually we design, models for different tasks, specialized single task models, including forward kinodynamics model. You have your patch, you have how you drive it, give you the next state, right? Or inverse kinodynamics model, you have a patch, you know where you want to go based on global planner, you give you how you drive it, your action here, right? Or you can do behavior cloning, give a patch, how do you drive it? So those are specialized single task models, which are not great because you need to train them separately. Usually they're very large. So how can we utilize the idea of transformers to do them all at the same time, right? So this is the idea of transformers. So we basically take a vehicle, as we mentioned here, so the terrain patch, the vehicle action, and also the vehicle pose. All these are the three modalities we put into our pre-training, transformer models, our transformer encoder. This is encoder only. There's no decoder here. We're only using the encoder here, right? By learning this, we will be able to learn the context vector, a context token of our transformer, and then that context token contains all the information about all these multi-model input here, pose, action, and terrain patch, right? After we learn this, all these context token can be used to predict the next patch. That is our pre-training task. If using our context token, we can predict the next patch, meaning our context token knows everything about everything necessary to do kinodynamic reasoning here. And then for downstream task, we can train each individual head based on their own training data, based on their own data. We can train a BC head, use the context vector to regress to actions, a patch reconstruction head to reconstruct our patch, forward kinodynamics and inverse kinodynamics to give us our next state and the action to drive to the desired next state. We can train those individually based on one big transformer encoder here, which works pretty well. That's our verticoder approach. So we also think about why what is the downside of verticoder, right? So this is our newest work, which is still on the review right now. So it's a data-driven and multitask transformer for off-road mobility. That is a full transformer. So the motivation here is the transformer in Verti-encoder still needs a lot of training data to achieve comparable results with SOTA model, like our TAL model. We still need a lot of data because transformers are notorious for needing lots of data to train, right? So we designed a new approach. We basically offload the intra-model relation learning into, basically for the three modalities: action, image, or you can say terrain patch, and the robot pose. Rather than treating them as separate modalities, we actually map them into the same, embedding space, which we call, this mapping to unified space here using a function called FS. And then instead of concatenating them as separate modalities to feed into the transformer as individual tokens, which is very data consuming, right? We actually concatenate the unified tokens here, which is much more efficient. We can actually learn this task with only 1 hour of data collected on our physical testbed. So that's one downside of Verti-encoder we are trying to address using our inter-model relation learning technique here. So the other is, Verti-encoder's downstream head is definitely smaller, right, compared to individual tasks, right? But still they need to be separately trained, right? So there's no shared information between different heads. Patch reconstruction is patch reconstruction. IKD is IKD. FKD is FKD. Behavior cloning is behavior cloning. There's nothing shared between them. We can train them each individually, even though they are smaller because of our transformer encoder. That is still not ideal. So that's also, we proposed another idea to try to mitigate that, called missing modality infilling. Here we are utilizing the transformer decoder. And when we are training the decoder, we can actually mask missing modalities. If we mask this pose here, if we don't give the encoder the pose, we wanted to learn what the distribution of this. And during deployment, if we mask the pose, it is basically giving us forward kinodynamics. If we mask our action, it will give us inverse kinodynamics. All these trains are just trained by one run. We mask 50% of action, 50% of pose. Then this whole transformer decoder can be used in a true multitask setting. We don't need to train them separately. And depending on which one we mask, it will give us different downstream tasks, in one training run here, right? So this is to give you an idea, the Verti formal architecture here. Right? You take the terrain patch, you take the pose, you take the action. Those are separate encodings, right? Instead of treating them as separate tokens, we use our FS function to map them into the unified representation space, which is a big deal here, which allows us to use only 1 hour of data in this unified representation space. We put into our Verti-encoder, generate our context tokens, and then rather than predicting the next token, we are also using the decoder for end-to-end training. We take the next 3 states, patch, action, and the pose, right? We can mask any of them by flipping a coin, 50% masking this, 50% masking this, and then we can train this using our cross attention, using our context tokens here in the Verti decoder, and we still use the FS to reconstruct our patch, action, and pose here. Right, so then by masking each of those during deployment, we will have different tasks. Masking action give us inverse kinodynamics learning. Masking a pose will give us forward kinodynamics learning, and masking both will give us behavioral cloning. Right, so then we will be able to do. This is one example by FKD forward kinodynamics. So by masking the pose, right, so then Vertiformer will just predict the next pose. Right, so we also put this in FKD in a sampling-based motion planner here, so we can roll out multiple FKD. Multiple steps for FKD for multiple trajectories. It will also plan a trajectory to go through this. Of course, so the performance is not as good as our classical approaches. There will be this is actually a failed case in terms of IKD. So we mask the action. So the transformer decoder will give us the action to take in terms of inverse kinodynamics. Of course, the next state is guided by a global planner. Say, hey, go there. What action should you take? That's what the transformer decoder will give us. So it's worked well in these kind of terrain, but eventually, I think here, it actually does not work very well because it gets stuck here because this hole here, right? It doesn't work 100%, but I just want to show a failure case here, right? But the whole idea is we can do 1 hour data to enable multiple downstream tasks in one training session here using this both encoder and decoder setup for the full transformer, multitask and also very data efficient. I think that's pretty much it, I guess. So we talk about high speed, we talk about vertically challenging. I guess before I take questions for vertically challenging, I want to play the final video here, which is the latest video. So let me ask a question. What if we combine these two? What do you think what will happen? You want to drive fast while your terrain is not even, right? So this will happen. So if you have uneven terrain, driving super fast, your vehicle will actually fly over, right? This gives us the problem, how do we control the in-air altitude when you are flying in the air with very limited actuation here, right? I want you to look at this video here. So this is the most impressive video. So if you go through this ramp, you can see the vehicle is launching at 90-degree roll angle, but it lands almost flat on the ground without damaging the vehicle because it's 90-degree roll here. So every time you launch, even if you have a different pose when you launch, you want to do in-air maneuvers with very limited controls because you don't have like a propeller, you don't have anything, you don't have a counterweight. The only thing you have is the throttle command and the steering command. That's everything you have, still V and omega, still throttle and steering. How can you control the vehicle in air? So we also did this. We built a turntable, a gimbal system here. We put the vehicle on there. So remember, there's no other actuation. That's the same car, very similar to F-110s. That's larger, that's a 1/5 scale car, right? So we only control the wheel speed, the throttle, and the steering, so it can achieve all these different kind of maneuvers here. So we did a bunch of different experiments. For example, rapid state change, compared to PID. PID is not very good. It doesn't really, it overshoots a lot. So we actually also use this idea of forward kinodynamics learning by rolling out a model in terms of the roll angle and the pitch angle, by looking at how should we rotate the wheels and also do the steering. And then we can actually do planning on top of that. We have a design state we want to go to. How do we plan to reach that within a very, very short time window? Because there's usually a very limited short window when the vehicle is airborne, right? So this is state stability, right? So Dom is our planner. Dom is because we named it after Dominic Toretto, because he fly cars, right? So FLY is an acronym for physics informed. I actually don't remember. So it pronounces as FLY, right? PHLI. So physics informed. Do you remember? I think what's the whole name of FLY? So basically, we combine them together. So we use the FLY model and then use DOM planner to plan. It's also sampling based planner, but with the constraint of you have only like 3 seconds air window. How can you plan within that to make sure it's actually working very well, right? So we also have trajectory tracking here. So if you have your goal trajectory showing blue here, right? So you want to track it within a given time. So we are constantly changing the goal. As you can see, the vehicle is able to do all the maneuvers and track it very closely. But with PID, it is not very easy because there's a lot of discontinuity in our state space here. Right? If you won't be able to reach this, how do you command so that you can reach it as quickly as possible? Or maybe you should go the other way around. For PID is only error driven, right? It doesn't have a model. It doesn't sample. So that's why it's actually get into like a local minimum very often here. Right, so this is time goal region. We want to reach a goal within a certain amount of time, but at right that time, we need to reach it. Not early, not late. Right, as you can see here, this is the goal. We are slowly driving the vehicle to reach that goal here. So this is the last video we made.
Done, cars go fly.
That's probably the last slide. So of course, collaborators, right, from A&M, from CMU, from UT Austin, all these people are working together on all the things you have seen in the past, and also of course sponsors we need to thank. Especially Army Research Lab sponsored lots of those talks, lots of those works we have dealt with in this talk. Right. I guess, as a summary, these are the two orthogonal directions we have been dealing with in learning extreme off-road mobility. And there's also some other works we have been doing in the lab, just to give you some, quick, idea. So perceptual degraded off-road mobility. Imagine you want to drive a vehicle into a dark forest, and you are not allowed to use any active sensing. So LiDAR is not allowed to be used. You're only allowed to use passive sensing. Right? For example, what we propose here is using thermal camera and event camera to enable robot night vision in off-road environments. And we also work a lot on this socially confined navigation as well. How do you drive a robot through those dense crowds? Those are delivery robots on our GMU campus. So after class, it does not perform very well, right? So we use a lot of data-driven approaches, machine learning as well. We collect data set with our helmet. It's called Musuhu, multi-model human social robot navigation data set. So we collect those data to train robots for them to navigate in those highly dense public crowds like this, right? I guess that's everything I got here. I think that's the last slide. Yeah.
Lots of exciting stuff. So ask questions.
I think there is one question in Zoom.
Yeah.
Yeah.
Ask questions in real life also.
Yeah.
Yeah, online people can also ask questions.
Are you monitoring chat for questions?
Yes.
Yes, yes.
Go ahead.
Yeah, then, hey, and that was to me or not, but I'll squeeze one in quick. Hi, Raul. Hi, everybody. Hey, just a question. When you're in those aerial maneuvers, and first of all, this is fantastic. I love it. And Raul, also, the future of
Yeah.
So I wanted
RoboRacer
to ask,
version.
so how do you close the gap between like the simulation and the real car, basically? Because the thing, so when we're like, for example, trying to test code, we notice that it's really hard to like, for example, like modelize like friction and like the environments, usually with the simulation. So how do you guys like basically close that gap?
So everything I talk about in this talk, we haven't used any simulation.
Also, it's
All
directly
this
test.
data are collected in the real world.
Well, okay.
Yes, so that is also one of, I'm not saying simulation so simulation is very useful. Don't develop this verti-bench thing, very useful in a lot of things, right? But here, so our philosophy here is, real world data is very precious, very expensive. So you need to use them very wisely. So that's why we don't really do too much end-to-end learning. You usually want to identify the right piece for you to learn. Then you can plug that learning piece into a big autonomy stack, like a big planet. So as you can see, we learn models a lot, inverse kinodynamics model, full kinodynamics model. So those are the techniques. So we intentionally limit our learning scope. So the very precious, very limited real world data can be used, can be very efficiently utilized. That's one. The other is you see this vertiformer idea. It's whole transformer, right? Transformers are notoriously difficult to train because they need a lot of data, right? So here, the vertiformer only use 1 hour of data. 1 hour of real world data. So it's okay for us to drive our robot on our indoor test bed for 1 hour. That's not too much of a trouble, right? But we investigate all these techniques, like all these two things, intramodality learning, projecting into the same unified space, and also this missing modality inferring idea. So that can make it very efficient.
I see. That makes sense.
And of course, then on the other side, simulation is very useful as well. So the whole idea of our verti-bench is, to evaluate off-road mobility is very difficult. Unlike evaluating state perception, that's very easy. You collect a real-world data set, you collect some data set, you benchmark against the ground truth, right? For off-road mobility, there's no ground truth. You have to run it, right? Run it in the real world is very expensive. And everybody have their own robots, have their own test course, have their own environment. That's very bad for standardization, right? That's why we have our simulator, the verti-bench. So we define this 1,000 tasks across 100 off-road environment we designed. Of course, the reason of choosing Chrono is also try to close the gap as much as possible, because Chrono is pretty high fidelity. There's a trade-off in the middle here you need to strike, because you want your physics fidelity to be high, but you also want the simulator to be run fast enough. Otherwise, it doesn't make sense for you to use simulators. Right? There are these, simulators like simulating like a suspension for 8 seconds, but that would take 5 days. That doesn't make sense for us to use because that's even slower than the real world. Right? You need to find the right spot here. You need to be fast enough for you to run your stuff, efficiently enough, and also it needs to be precise enough so it won't give you too much opportunity to look at.
That makes sense.
So we saw a scenario where the vehicle actually went to a ramp and it lost the traction. And you actually also showed us that the sampler was planning its motion, how it's gonna be when it's in the air. So basically my question is like, suppose if the sampler is working, it has to pre-know the states or basically the physics of the system to pre-plan in the future. So, but when the system is like on the ground, it might be using a certain different set of physical equations. And when it goes into air, that equations might fail.
Yes.
So how is planner like adjusting itself?
So right now, the process is not happening. That is definitely the next what we want to do right now. So it is given to a different set of equation by a manual trigger. So Anika was driving it. When it's in the air, switch the trigger, so go use our planet. So of course, that is very preliminary work, right? So the final goal of this would be developing a set of, as I was talking to Rahul about this like an hour ago. So it's multi-model kind of kinodynamics, right? The whole kinodynamic space is SC3, right? We can learn the entire space or can decompose them into different models, right? So one model is driving on flat ground. One model is driving on very rugged terrain. One model is flying in the air, one model is on like wheeling, right? So the back wheels on the ground, front wheels in the air. One model maybe like balancing on the side. So those are different modalities. And then we need to figure out how to switch between these models and design controllers or planners for each of those models. Multi-model kinodynamics learning. I would say that is definitely a very good future work direction.
So are we talking about like trying to build a network that could learn everything, a universal model and then, yeah.
Yes, if you want to, that would be ambitious, right? Because if you want to learn a network that can work for every single of these models, again, going back to this data question, do you have enough data to cover all of them, right? If you can have data, great, you cover everything. So my perspective is, if you don't have enough data, you need to be using them very efficiently. That's why decomposing the whole space into like small regions and then collecting data, learn for each of the small regions, that will be more efficient. And then just try to figure out the connections between all these different models.
And also, like in future, are you guys planning to bring in RL into this stuff? Sir?
Yes. So one of the work Tom did, I didn't talk about, but I only briefly mentioned this Verti-selector is using RL. So how do we efficiently learn in Chrono, in the simulator, so you can learn the mobility thing, right? So what he did is so using curriculum learning. Yes. First of all, it's not Isaac Gym, it's not parallelizable. For our Chrono, again, the trade-off between high physics fidelity versus speed, right? We want to strike the balance in the middle. That means it's not very fast. It is also precise enough, right? So we need to be very efficient. So what Tom did was trying to use curriculum learning. So we don't just blindly generate lots of simulation environments, let it train. We try to figure out what's the next environment for the robot to learn based on the robot's current capability. So that's the whole Verti-selector idea, to build a curriculum to train the Verti wheels in simulation so it can be more efficient.
Thank you.
Yeah, there's a question by David online. When you are in the air,
So we are actually using braking, right? But I guess we can, in this video, we are not, right?
Yeah, I mean, technically we are using brakes.
We are,
The model
right?
itself decides whether to accelerate or
Or
brake.
decelerate,
Yeah,
yeah, we do it. So braking is basically decelerating, right? We are definitely using braking. By decelerating, you can pitch the
It
vehicle
really
down.
depends on what is your current pitch angle. If you're at like really big angle and it's easy to brake rather than accelerate, then it would be better to brake.
Yep, yeah. Yes, slamming a brake is definitely very effective for adjusting pitch in the air. We are actually using that, right? There's also this like which direction you want to go. You want to brake to go down, or you want to loop around to depending on the state. That is why PID is not good, because PID is only doing aerodrome, right? Well, we can plan over this. We can figure out, is this way better or all the way around better?
We found out it's actually 6 to 7 times more responsive to brake instead of accelerate, because you can brake really, really hard, but you cannot accelerate that fast. But it really depends what's your current speed. If you're already at nearly zero speed, braking won't give you any inertia. Yes.
Did you figure out explicit equation of motion for the kinodynamics of the car in the air, or you simply use that with the neural network?
But so if you go to the paper, we have derived all the physics, very detailed physics. So there are two effects that is governing all these universe. One is called the inertia effect. You rotate the wheel because of inertia, you will have the pitch, right? The other is called gyroscopic effect, because your front wheel is rotating. And if you have a torque perpendicular to your rotating axis, you will have this this effect called precession. Then that precession will give you another torque to your running pitch. So we do have all the physics there, but the problem is, how do you estimate all the quantities in here? Like for example, you need to know the moment of inertia of your wheels, right? That is not easy for you to estimate, because when you quickly turn the wheel, they also expand. It's not even constant. So eventually, after we derive the equation, we decompose it into two different parts. So from the action all the way to the, I think it's the roll dot pitch dot, right?
Yeah.
So the roll angle, roll speed, acceleration, or
Roll acceleration.
roll dot pitch dot. So from the action to the acceleration of the roll and pitch angles, we are using learning, and then after that, it's just integration. So those are physics equations.
So I wanted to ask, so did Professor Raul and you thought about like making RoboRacer with this kind of car of what you call with off-road driving racing? Do you guys thought about that?
That would be a very fun thing to do. We're definitely thinking about it.
that's why we have
Sorry.
Shuesu right here.
I see.
I mean, that's the plan, and there are other friends of ours, common friends who will talk to in the afternoon, who also want to do that. But I think the idea is first we develop the algorithms, we integrate them in the RoboRacer stack, then it can become in the competition.
I see.
And then people can either improve on those baselines or make their own, but at least we have a working solution, we have some sim environment. And again, I think, we don't want to go too crazy with the sim environment. We will have one, but as he said, you have to have the real
Yeah,
stuff.
yeah, yeah.
And so there are some, so that's the idea. So we go to non-planar and then we go to off-road and then there is this discontinuity, that we have with the control. So that's sort of the roadmap of going forward. So whoever's interested in that stuff, you can work with us together. Shuesu is not so far away. His team is, George Mason University is just very close by. And if you're interested in capstone projects, independent study, master's thesis, we define all of that. We do experiments in Pennovation. There's a skate park, a Sai over there. He's already scanned it with the 3D LiDAR. There is an off-road racing track just in Fairmont Park, just like less than 1.5 miles from campus. So you can, so there are all these sort of places. We have to go out and do stuff. We can't just be sitting in our F110 gym and doing that, right? So the couple of other things I wanted to mention, for the final race, the track is ready to set up and use, and I will give you the instructions for in the Pennovation drone cage. It's a big space. We'll have a big track, and we just went to test out the ground yesterday, and it's fine. There is no big gradient or big bumps, and then we have the yellow track and the black track, so we can use that to set it up. And once the TAs will come to set up with the teams, and then you'll have that ready to go. The last announcement is, and I'll send an ed post for that, and then y'all can go there, set up the track. You just keep telling us on ed, okay, we are going now, because it is some distance there, and then you have to set up the track, pull it down, and we'll give you instructions on how to do that. And then the last thing is that today's was off-roading, and then on Wednesday will be the last, guest lecture for the class. That'll be on RL for racing, and that's all the ETH Zurich guys who have been part of RoboRacer for many years. They'll talk about, they have again many papers that they have done with RL for racing, and so you can get to learn from that too. But let's give Professor Shuesu. Yeah, this is not just some guest lecture. It's sort of like you can get involved in doing real research after this, right? So it's just broadening. We're not really only interested in ground vehicles. This starts to blur what is ground, and then we'll have ground and drone combinations so that you can, actually have more downforce, reduce downforce, all of these combinations. And then Professor Antonio will be also working together with us. So lots of exciting stuff coming up. We'll continue on.
Great, really.
Yes, I just remember I have a slide.
Oh, yeah,
actually, I put a
This
kind
is
of
like,
she
just
when you're there, I can also. Yeah.
I have